Hello, my friend. Today I'd like to talk more skills with the how to write with the internal assessment. So this is now the fourth video, and the title goes with the "Sell me this pen." Okay, it's inspired by the line from the Wolf of Wall Street. So let's get to it. So yes, so this is the very famous line from the movie, right? He goes to the salesman and sell me this pen. It's checking on your sales skills, how to win someone's mind so that you can play your favor. And turning around your table for your favor, right? So that is, I think, the essence of internal assessment. So without further ado, let's get started. So the very first thing I like to talk about, well, actually the foremost, one of the topics that I will talk about today are mostly heavily concentrated on the differential equations, and there are topics related to it, and it's very popular, so please do not write this topic the way I talk about it, okay? Because it's going to be presumably for everyone, right? So let's have a look. So the very first popular example that people write about their internal assessment is called the law of cooling, right? So then, law of cooling associated with this differential equation, mathematically speaking. And if you are solving the differential equations, then, if this is for the HS student, it's in the syllabus, right? Well, how would you solve it? Yeah, you're right. You know how to solve it using the separation of variables. This is a very typical technique, isn't it? So now I go to the differential equation. So now I'm going to match the dependent variable and the independent variable separately, because I can think of it as the ratio, as the derivative as a quotient. No problem. So I got that. Then I would like to do the integral. And then on the left-hand side, I got a rational function. And the rational function integral will just result in the logarithmic function. And you can exponentiate both sides. Then you got to get the exponential function. Easy peasy, lemon squeeze. Okay? And that is not the way you should write for your internal assessment. That, my friend, is not the way you should narrate the method of the use of mathematics for the IA. Don't do that, okay? You can do that after, you can do that if you don't skip this crucial part that I'm about to talk about. Every math book tells you what you just did with the law of cooling, with the separation of variable. Why should your paper be any different, you see? And what if as a reader, what I can say is, oh, okay, I get it, it works, I see there is a solution, but this is something written in many publications, many textbooks. Why would you talk about that, right? That's not how you do it. That's not how you should write down the internal assessment. And so let's talk about why we needed that equation first of all. So we saw, right, that the differential equation for the law of cooling, all right, was given as the rate of the temperature of the object is proportional to the difference of the temperature and then the environment temperature. So that's the typical law of cooling equation. So before coming up with the equation, before mentioning, oh, Isaac Newton said it before, oh, I got it from this textbook. No. You should sort of involve your personal engagement on this. You know what? Let me tell you what I mean by that. First, before we talk about that equation, if your paper, it can be two different topics of the IA paper. It can be purely theoretical, or it can be purely theoretical, or it can be like a applied mathematics, right? For the analyzing the real life case. And imagine that you were, for example, drinking coffee, right? Imagine you were drinking coffee in the room, right? And then you somehow wanted to see what function would represent the temperature change of that coffee, right? And for me, it's very difficult to find an exact function, not exact, but very good function to explain the change of the temperature. To explain the change of an object is actually very difficult, because you need to know the answer already. I don't know what function this is going to be. I'm sure if you leave the hot coffee in a relatively, lukewarm temperature, let's say 20 degree, and the coffee was like, let's say 60 degree, very boiling hot, I'm sure it's going to decay, isn't it? Right? But I don't know whether that decaying function is going to be given by quadratic, cubic, polynomial, rational function, logarithmic function, or exponential function. I don't know this. I don't know it. Therefore, what you then need to explain is, I like to see what function would represent to change this, but I don't know the function yet, right? But what I could do is to narrate. You can state what observations you had from that situation, right? So if you look at the temperature change, so not just the temperature change, but you like to talk about how fast it changes, isn't it? So now, imagine you left the hot coffee in a very ice-cold environment. Then it's going to change very fast. If the difference of the object and the environment is very large, the rate is going to be changing very, very fast. Okay, but let's leave it in a desert, in a very, very hot temperature. then you know the difference is going to be very, very small. Hence, the change of the coffee is going to be slower than it would have been in a very ice-cold environment. And what I'm trying to suggest here is that we cannot take this equation for granted. You see, if you were to write applicable, applied mathematics for the real life situation, you shouldn't just quote the equation from a textbook. You see, you have to give your personal engagement of how to derive that equation. Suppose that you didn't know anything about the law of cooling. You see, I just wanted to talk about the change of the temperature, but for me it was very difficult. But now I like to talk about what observation I made while experimenting with this temperature, and I saw in a different environment the way it changes, you see. The rate of change changes. But how does it change is what we have to personally reflect and then show to the reader that you gave your reflection before coming up with the rigorous mathematical answer, you see. Then you need to come up with this. Newton is not going to help you. You cannot quote the Newton if you want to improve your personal engagement. You have to do the personal experiment. You have to give your personal reflection on it. Now I got this. I don't know if it's true. See, I don't know if it's true. I think the rate of change of the temperature must be proportional to their difference, because that's what I saw, right? This difference could be square minus e square, who knows? But I'm just saying it because that's my observation. That's what I learned from the calculus, that if it's something with the rate of change, I would like to associate with the derivative. Now I got a differential equation. And then, after having made those personal engagement, personal reflection, you can then give a justification of doing the research, of doing a reference for your topic. So after having written this down, what I'm going to say is the following. Oh, okay. I'd like to actually verify my claim, because I could have said this is y squared minus e squared. If there's nowhere to check, I would have solved that equation, which is going to be much more complicated because it's not a linear differential equation, you see. But yeah, then you can say, okay, I actually wanted to verify my personal reflection, so I researched it. I researched about the temperature object change and if it's really proportional to the difference of the temperature, and it turns out to be true. You see the big difference here. Instead of opening your topic with the quotations such as, oh, okay, while I was glancing through the potential topic, I learned something called the law of cooling. I like to use it. In this equation, there's a linear differential equation which was a homogeneous case, and it uses a separation of variable. So I like to use it. It is not the ideal way of writing the IA because it really minimizes your personal engagement. But supposedly, you knew what you were going to write about. Obviously, when you decided with this topic, you knew you were going to talk about the differential equation and etc., right? And you knew already about the law of cooling. But you need to pretend naively saying that, oh, I didn't know about this equation, but, I like to talk about my coffee change. I don't know what function is going to represent for the change of the function, but what I like to do is to talk about how fast it changes and give my personal reflection to it. You see the sudden change in the niche and the tone. That's very important because you have to rub it in your personal engagement. And then writing this down with the separation of variables is completely okay because your mathematics has to be rigorous. You're not inventing any new technique. But now, thanks to your personal observation, thanks to the verification by Newton, now you can continue with this correct differential equation and solve it analytically, right? So you shouldn't be the judge telling the reader what you're going to do, right? You have to be a detective, finding the clue. Sometimes fail. You shouldn't be always successful when you're writing about the IA because, how can you be? Unless you know what you're going to do. Unless you know whatever the verdict you gave will be truth, right? We don't know that, right? So hence we call it personal engagement, right? So it's very, very important. Then you can work on the differential equation. So then, you see, instead of being a judge, instead of referencing the textbook from the start, you gave a sense of detective, and then you can refer to the wise guy. You can refer to the textbook then to verify your claim. But that claim must be thoroughly appear to be from your personal reflection, not from the textbook. Okay, is my advice. I'm not saying it's the ultimate truth of writing the IA, but this is what I think the paper as a high school student should be writing. Your enthusiasm to learn and then your passion of curiosity has to be appeared, okay, on your paper. And that can be only done so when you write down your personal reflection, not reference, not quoting. Okay, let's have a look at another second very popular example called the logistic growth. Yes, it's also in the syllabus for the AA, right? So and also AI. And then, the solution to this is how to solve is also the separation variable. Not only does it require the separation variable, it also requires a partial fraction, right? You need to separate the fraction, and then if you, use the property of logarithms exponentiation, you can derive this typical logistic growth function, right? With the sigmoid shape, right? That's what we have. But as you know, that is not the way you should write. Everyone knows what the solution looks like if you just Google it for 1 second. It doesn't matter. It does not matter how you solve it, but it matters how you can derive that differential equation is much more important. So let me quickly show you by the video. So, what you want to know is, again, you want to know how the population sort of looks like, right? You give your thought, right? You want to talk about the y function. You want to talk about the solution. However, I don't know what it's going to look like, right? But I can talk about how fast it's going to change. That can be done by personal reflection. At the very early stage of a population, obviously, it's going to change very slowly, isn't it? Hence, I claim my rate is going to be very, very slow. It's going to be around here. It's going to change very, very slow. However, the more people we have, the more married couple there are, hence more children there will be. The more children we have, the more population it's going to be. It's going to be, blossom, right? So then let's have a look. So then, yes, up until a certain stage, it is going to go very fast, right? The rate is going to get bigger and bigger as we have more population. However, I have a problem with that. That indicates that my rate is going to be exponential, isn't it? The more population we have, the more time, the faster it gets, faster it changes, hence exponential. But that has a problem because it's going to be, what is it? Yes, divergent to the infinity. I don't want that. So at certain point, what I need to do is to sort of, slow down the increase. I need to slow down the increase. Hence, my rate is going to actually slow down like this. Good. That is my observation. That's my claim. You see, I'm not quoting, I'm not referencing anything. If I think about the ideal population, I can think about what? Okay, it does increase very fast, but after a certain time, I cannot keep that on going because the population is going to be infinity. But instead, I like to control it so that it's going to change slower so that we don't reach out to infinity, but something called the carrying capacity. But I don't have a differential equation for this. You see, I didn't start with the population over time because I know nothing about it. But I can talk about how fast it changes, you see. And from this, what we then can observe, what we can say with the personal engagement is to say, oh, okay, this function looks like a quadratic function, you see? So for me, what I would have claimed is, okay, for my differential equation with the derivative of a population, it looks like what? It looks like a concave down quadratic. So what I would say is, oh, okay, what if I got the, zero gradient here, and then, zero population there, and then I got the maximum capacity here. I claim that must be my differential equation. You can claim that from what you have observed. And what would you do? Yes, then you will, justify by researching it, actually, right? Okay, this is what I think, all right? And then I wanted to verify this observation by another source or reference. And then the new ways to derive new techniques that you're going to be learning on the way will be justified because you started with your own. You started with your own observation, own reflection. And then you can solve the differential equation using the separation of variable. The next video looks like this. So now we had the derivative, and then from the derivative, the solution is going to look like the logistic growth, where we know that it's going to be, changing very, very fast at first, but after the inflection, which is going to be half of the population, it's going to converge to, the carrying capacity. That's the typical sigmoid shape, but that is not important, because from then on, it's going to be very typical. Every textbook with the population growth has this logistic growth. But what is going to be more important for you is why you needed it. How you came up with the differential equation before, instead of stating that I got it from a textbook, right? You have to you have to pretend that the idea solely came from your original personal engagement. And that is important how you write. Okay? And then, let's talk about the third one. Another third very important topic for the differential equation is called Hooke's law, because it's the second order differential equation. So let's have a look. So now let's check this out. So I want to solve this differential equation. I want to solve this differential equation, and how you would do is let's think about it. How would you solve it? Because it's not in the syllabus, you see. The second order differential equation is not on the syllabus on the AA, but it is on AI. because they know how to linearize things with the coupled linear differential equations, so no problem. How will you solve it? Right, but what you can do is, yes, there are many techniques of solving the linear homogeneous second order differential equation, something called the auxiliary equation. However, you're not going to mention that. You have to actually try yourself for solving this differential equation. And what have I mentioned? Every step you write doesn't necessarily have to be true, you see? But as long as you give a meaningful personal step, personal analysis, personal reflection, then it works, you see? So let's have a look. So this is my second order differential equation, right? And then can we, what you would like to do with your personal time is the following. What you could have done is, okay, I like to find the, a function whose second derivative is going to become itself, you see? And does polynomial work? Maybe not. Maybe not. Does the sine works? First derivative doesn't work. However, if you differentiate the cosine, it certainly does go back to the sine, although it's got the different multiple, but that's okay. We got some constant multiple to verify. So the sine function seems to work. What about the exponential function? Well, if you differentiate twice, it works also. Oh, okay, that sounds really great. What about the logarithmic function? Well, unfortunately, if you differentiate twice from the log, it becomes sort of a rational function, which may not be the best interest for our solution, you see. So this is what you have to do. Before you talk about a very analytic solution, you still have to give a try about how you would have worked it out, right? And the very first thing I would have written when I'm dealing with this differential equation, I try, okay, I like to use some of the elementary functions that I learned from the syllabus. And then what would be the second thing? So I found two. What would be the second thing? Well, okay, just because I found these two doesn't mean that they are the unique solutions, right? What about the sum of it, right? The e to the power of x plus e to the power of 2x. If you differentiate twice, I will have some constant multiple. No problem, but I will still have the same sort of a style, right? And then you can get into those tales of the, all the questions that leads into the analytic technique of solving such equations. But you cannot refer to the analytic method right away. You have to give your personal reflection on it first, okay? Another very typical Hooke's law for the popular IEA topic is the following. It's with the damping force. So right for the ideal case, the elastic will go infinite many times, but it is not true because there will be some friction, right? There will be some air resistance, whatever. So then obviously these oscillation will slow down, right? So very nice visual for you prepared. So as you can see, those are the displacement, velocity, and acceleration. As all you can see show the sort of a damped oscillation, you see. So it is a periodic, but the amplitude is gradually going down, So that's, I'm sure it's going to be typically, product of the exponential decay function and then some sort of a cosine or sine function, you name it, right? So, and this is actually very, very popular function form that you have seen in calculus. And there's a reason, because it's actually a solution to this the Hooke's law or the wave equation. But, can be obviously written for your IA. But let's get back to it. So now we got, damping force is the friction, and it's proportional to the velocity, right? Because if you put your hands out of the window, the faster the car goes, the stronger the wind it blows against your hand. That shows that the resistance is proportional to the velocity. That's why I added with this force. The resistant force is proportional to the velocity, which is the derivative of the displacement. You don't have to worry about it. Don't worry about that. But now I got this differential equation, which is a lot more complicated than last time because of this such factor. And then what would you do? Okay, yes, if you type in the wave equation, every textbook, every source tells you what to do. They ask you to use auxiliary equation. And if you use auxiliary equation, you can make the equation into some sort of a polynomial form where you got the roots of the polynomial term, which you can then use it for the general solution of the function. Sure, it sounds very advanced technique. That is, I think, very nice for the IA. It seems like it's using a lot, but it's really not. It's using calculus and then the function that you already have learned. However, that I don't care. I don't care that you know about the auxiliary equation. It's not about how much you have. It's not about how much you know, but it's about how you have come up with that equation with your own story. You have to give your sort of sense of life of pi in your writing. You cannot say, oh, I got the second order differential equation or homogeneous case, and I like to use the auxiliary equation. Is not the way you should go take your step forward if you see advanced question like that. But what you need to do is, you like to try out, for example, like we did from the previous case. And it seems like what? This time, I think sine, although it could work, you see, because this is going to be sine, and sum of sine and cosine can be put it into the sum to product formula, or sorry, sum of sine and cosine if it's got the same period, and then work it out together. But also, exponential looks really, really nice to me. You know why? Because even if you differentiate many times, it's going to preserve the form, you see? And in fact, if you let the y is equal to e to the power of lambda x, and then if you differentiate twice and once and the same thing, it's going to still have the same of e to the power of lambda x, e to the power of lambda x, e to the power of lambda x. But if you differentiate using the chain rule, you know those constant coefficients must come out twice. For example, for the second derivative, first derivative come out 1, and here I haven't differentiated, it just becomes nothing. So if you cancel out this out, then you know you get a quadratic equation out of it. You see, you knew nothing about the auxiliary equation. You knew nothing about the auxiliary equation, you see? But you give a personal reflection, you see, to justify for one. You made a very interesting observation. I had a second order differential equation, and I wanted to see if one of the elementary functions that I know works. Indeed, it does work with the exponential, but somehow it doesn't give the solution right away. It gives you some sort of a quadratic equation, which we can solve it by using either factorization or quadratic formula. And that also has a different types of a solution, isn't it? We got the two distinct real, one repeated roots, and the two distinct complex roots. But now what you can do is, okay, I made a very interesting observation. Suddenly I'm dealing with quadratic. Is this true? Am I going the right direction? Then, my friend, you can justify. This is a justification in Korean. Justify. You can justify your research. That, my friend, is very important. Because you cannot just say auxiliary equation, I like to solve it. You can do it, but every textbook can do it too. Why should your paper be interesting? Because you came up with your own personal reflection, you have a hardship, but you know which direction you go. Because you know which direction you go, you know how to hurdle it. And you know how to jump on it with some help, with some little bit of help from the ancestors who already have solved it for you and then define it for you. And then you can refer to those things, right? You cannot start with the reference because that will really lose the personal engagement and justification, the righteousness of writing the paper. Now you can investigate with auxiliary equation then you can come up with this, and then you can then list out the general solution. That's okay. Okay? So you have to always give your personal reflection. The last example that I like to talk about is another very famous differential equation that does not have an analytic solution, and hence it uses the Euler's method, which is also in the syllabus. Very, very popular model for the SIR. And if I have a friendly advice for those of you who are interested in writing this SIR modeling, please do not write it. Do not write about COVID. Please don't do it. Why? Because imagine 200,000 people taking IA, IB every year. Everyone takes math. Okay, it's a mandatory subject in topic in subject 5, right? In subject 5, you cannot be one of those 100,000 people writing about COVID, because if you think about the IA internal assessment, what's very tempting is the one that it's got that data analysis, when you have the data and analyze on it. But very common thing is like the linear regression. Please don't do it. You're gonna you're gonna have horrible result on the use of math, regardless of SL and HRP, because it's very, very rudimentary. And then the SIR modeling, because of COVID, everyone does it. But please don't do it. So it's too popular to. But if you do insist, please let's do it right, okay? And then why it is important is, again, you're not going to say, oh, SIR modeling is given as such, according to NHS, whatever. No. You cannot come up with that differential equation, okay? What you have to do is to be able to explain, you see? Again, what we have mentioned before, it is quite difficult. It is quite difficult to talk about the function. So what you like to talk about is how we can come up with the rate of change. How does the susceptible population change? How fast it changes is what you want to talk about. Like, how will you talk about it, right? Instead of saying, I got this equation from such. Right, so, it doesn't matter whether we know this equation. It matters whether you can build on it by giving your personal reflection, you see? You like to talk about how fast the susceptible changes. It's probably better if I show you by the graph. Okay, let me quickly show you the bar graph. And you need to show why the rate of change of infection looks like this with the rate of change of susceptible, and then this is the rate of change with the recovery, where the recovery comes like this. Okay, where gamma is the duration, one of the duration. So why? Why does it look like that? So let's talk about why it's going to look like this. So first of all, when you want to talk about the rate of change of a susceptible, why are we talking about the rate of change? Because to know the function itself is very difficult, but we can make observation how fast it changes, starting with the differential equation, you see? So you see the susceptible people, you know it is going to change, it really depends on the number of, I mean, there are many, many factors, but in the ideal situation, many, many, conditions, it will depend on the number of contacts, you see? If you have many, many people contacting each other, then the people who haven't got the COVID yet, who wasn't infected with the flu, is going to drop very fast, right? Because if you get in touch with many, many infected people, it's more likely that it's going to spread out. So what we can say here is rate of change is going to be proportional to the number of contacts, right? That is one of the many factors, right? But the typical SIR modeling you do is the one with the number of contacts. So it is proportional. But how do you get the number of contacts? Sure, the way you get the number of contacts is to get you get it as a product of the susceptible and infected, because one individual one individual can meet with all the cases of infected. So this is independent cases. That's why we put it into the product. However, I cannot say every contact will matter. You see, not every contact matters. So what you need to do here is to only get the proportion of those contacts. So that is the infected rate. You see, you need to build up those differential equations. You have to explain how we can come up with this, and then whether our logic of coming up with such equation is correct should be justified later with whatever the articles you refer to as a sort of a validation. Right. And then what you can do is, of course, it's going to drop. The health people will, decrease as we have more infection. Hence, we put it as a negative. Okay, but here, as you can see, not only should thus be depending on the susceptible, it also depends on the infected population. So now I need some equation for the infected rate. Infected population. So for that, I don't know it. So I like to talk about the observation that I can make with the rate of the infection. So rate of infection obviously is going to be, it's at first exponential, right? It's going to change very fast. So it loves number of people contact, right? So if you have number of people contact, the more you have, the better it is, the more increase it's going to be. Hence, I want you to notice the difference with the positive. You have to explain that. You cannot just say this is the equation we have. You have to explain why we have a positive, why we have number of contacts also for the infected rate, right? More people in contact, better it is for the infected rate. However, in that case, again, this is going to be exponential growth, right? Susceptible would have been exponential decay. However, for this one, you realize that means everyone is going to be infected. Everyone's going to then, die out. We don't want that, you see. Obviously, some people will recover. You see, and therefore the rate of the recovery must be taken into account, right? So that you give your personal engagement. What you would have said for this differential equation is to say, okay, infected people, we obviously depend on the number of people in contact, but obviously we get people getting fast recovery, and if you assume so, then they don't get the COVID again. Well, of course they do get. So obviously that situation is a lot more complicated than the ideal case like this. But if you just stick with the ideal case of the SIR, you got to get the recovery rate. Okay, therefore I get the recovery rate. What's going to be the recovery rate? Well, the people, the more infected people, right, the more people to be recovered, you see. Hence, it is going to be, what is it? Proportional to the infected people, you see. Think about it. More infected people, more people to be recovered. Hence, the recovery is going to get faster and faster. Hence, we make this directly proportional assumption. I don't know if that's true. Then, after having mentioned about those personal engagement, you can then refer to the outside source indicating that it is true. And this gamma talks about the recovery rate. It depends on the duration of the disease, right? The longer it takes, less likely it's going to recover, the slower the rate is, right, for the recovery rate. So that's a reciprocal of the duration. And if you tell me, why did you decide 1 over d? Well, you may not know. Then you can refer, why is 1 over the duration is actually the recovery rate? What's the mathematical reason behind it? You can then refer to the reference, you see. But, that is justified because the wise guy, the old wisdom will tell you why we have such rate. And then what we can show here is the result. So now we'll put that in the proportion for the good scaling. As you can see, the susceptible population is going to look like the following. we had 100%, or let's say 98% of the proportion of the susceptible in the entire population, but because of a small portion of the infected, susceptible will sort of die out. Then we can talk about the infected. The infected will, will grow very fast. However, I cannot say everyone is going to be infected. Some people will recover, and that's going to slow down the infected rate, and hence it becomes, it dies out also. Therefore, recovery rate, at first, there are not many sick people, so it's going to be very small. However, as more people, the more people get infected, more people will also recover, and then also the how fast it changes will sort of get stagnant as less people get infected eventually. And that's the typical, SIR modeling graph. But the reason I'm saying here is you cannot just say, okay, there is an SIR modeling like this and I like to use it. No. You have to explain why you got such differential equation. Then you can use, technical method like the Euler's method to sketch out this curve, which you can see in many textbooks, many references. That's not the importance of IA. The importance of IA is how you can show your personal reflection everywhere you write. That's the most critical part. Okay. But let me tell you the top secret, the pro tip for the IA. Aside from whatever I've mentioned, this is actually the most important thing. What I'm about to tell you is the most important thing. Everything I've talked so far does not matter unless you know your teacher. Okay? You must appear your teacher first. It doesn't matter what I've written about, what I've mentioned about. Some teachers love it, some teachers don't love it. It comes down to their preference. So IA or English essay, it's really difficult to mark or prepare unless you are prepared with teacher's predilection, their preference. You must know what they like and how, especially not just about the topics, but what they want you to write, how they want you to write, the style of writing. And that can easily be seen prior to your writing assessment, your written assessment, when you refer to some of the people who already have graduated from the same teacher. That's one way to sort of already see what your teacher wants. Whatever I mentioned, all the technique really doesn't matter unless you know what your teacher wants, okay? That's the most important thing. Okay? So please know that first. And then they can love you, you see? You think they are very mean, like Professor Snape, but they are going to love you as always. They do have that strong bond with you as long as you show your passion to learn too. And also engage during the lesson, especially when you start writing about the IA, please refer to the critical feedback the teacher is giving to an example and make sure you don't make the same mistake, right? And then you can refer to one of the techniques that I mentioned as a supplementary technique. The primary technique is you know your teacher and you know what they want, okay? Yeah, but that's very nice, sort of 4 examples just based on differential equation because they are very popular to write about the IA because somehow it turns out, school loves like the math IA with the practicality. For me, it doesn't matter. It can be purely theoretical. It should be allowed. In fact, matter of fact, it should be more popular with the theoretical for the math IA, but it's easier to mark if you got the real life. So nowadays, it's becoming more like a physics IA. But nevertheless, you can still go through, overcome with this personal engagement, your deductive skills, deductive thinking on your writing, and that's the tip that I wanted to give you. Okay? So that wraps up the 4th class on the IA. That's pretty much it for me today. See you next time.